So there are many times in this course where I'm going to describe something as being magic to you, and so say how borohydride reduces a carbon-mercury bond down to the carbon-hydrogen bond. And when I say magic, what I mean is you don't need to know how it works. And in some cases, I know how it works, and I'm just not sharing because it's not part of the course, it's not really that important. And there are times when I really don't know how it works because it's complicated, and there are definitely times when it's not known how it works because it's so complicated that we haven't figured it out yet. I'm not entirely sure where the borohydride reducing the mercury falls, whether it's basically something that I'm not quite on top of but I really should know, or if it's more of the, yeah, we really don't know how it works. I would like to think, obviously, it's closer to the latter, but there are other things that I would like to tell you about, and the reason to have a video like this one is because the way that borane behaves turns out to be really important for later in the course, and so though I'm not going to show you the exact details of how the magic itself works, I do think it's important to talk about borane itself and borohydride and back and forth between them because that will illustrate something that will be really important really soon. So the first thing I want to point out for borane, which is to say BH3, is that boron brings 3 electrons to a Lewis structure, hydrogens each bring 1, so if you have BH3, there are only 6 electrons total in the molecule, which means that this boron has an empty orbital right here, and it lacks an octet. So right there is an empty p orbital, and boron is not happy at the moment. Now, not happy is a bit of a misnomer. It has only 6 electrons around it, but it is formally neutral. In other words, it lacks an octet, but it is formally neutral. Now, in the presence of some source of adding H minus, you could, and this is not how you make it, but you could make BH4 minus, something like that. Now you see a different problem. Borohydride, as drawn, has a full octet, so in that sense it's happy. On the other hand, the boron now has a minus charge on it, and boron is to the left of carbon, and if carbon doesn't want to have a minus charge, you better believe that the boron does not want to have a minus charge. So what this does is essentially act as a source of H minus. And again, I never really want you drawing H minus, but we have several different reagents that act as sources of H minus, and borohydride, BH4 minus, is one of them. And so in other words, if you could lose an H minus, you would go back to borane, and in some sense you'd be happy because the charge is gone, but in another sense you wouldn't have an octet. But if you gain a hydride, gain an H minus, then now you're at borohydride, and you have a full octet, but you also have a minus charge on the boron. And so boron, in some sense, is not really happy any of the time. It's either needing a full octet and gaining something, but as soon as it has a full octet, then it wants to lose something, and so it really exists kind of somewhere in between there, and it reacts that way. It wants more electrons, but it also wants to get rid of electrons, often simultaneously. Just to draw out something weird to show you about this, what I'm going to show now is borane from the side, and again, I'm trying to illustrate where the extra electron density would go if it were to react that way. And so what we have now is an empty orbital, and this is an empty p orbital because what we have here is a sp2 hybridized system. But the way borane is going to interact with another borane is you'd have another borane come along, like say down here, and you'd have these hydrogens kind of overlapping with the empty orbital like so, and you'd have the empty orbital on the other borane overlapping with a hydrogen like so. And so what would happen here is this electron density from that bond may want to kind of flow into that orbital, and that might help. And likewise, you might want to have electron density from that bond kind of flow into that orbital. And where you might end up is in something that we call diborane. And this actually exists. And really, one way to think about what I'm drawing here is that the borons have one full bond and kind of a loose interaction with another bond at the same time. And again, the reason why this molecule exists is because borane itself lacks an octet, but borohydride is too reactive because it has an octet. And so what you'd love to be able to do is kind of exist in the middle there somewhere. And so boranes will come together and kind of share their electron density with each other and create what we call 3-center 2-electron bonds, which are definitely a weird thought and definitely don't fit our standard Lewis structure picture. So at the moment, what I've done is drawn a full bond between this hydrogen and this borane, and a loose interaction between this hydrogen and this borane. But kind of the way it behaves is as though you had bonding all through this area, but there's only 2 electrons and there's 3 atoms, and likewise you have bonding through this area, and again there's 3 atoms, boron, boron, hydrogen, and 2 electrons for the entire place. So what does B2H6 look like? Well, we know it looks like this. It exists as dimers, although it kind of behaves like separate entities these in some senses and other stuff. So anyhow, it's complicated is what I'm saying. So when I go to tell you that I don't know exactly how borohydride works, bear in mind it's in the context of this, that it's already doing weird chemistry anyway, largely because it has an empty orbital, but as soon as it fills that orbital, it becomes negatively charged. Now, the reason why this video exists is because of precisely these facts. We're going to use borane in this course to perform chemistry that depends on it being able to accept electrons from another source, and as soon as it has accepted those electrons, it immediately wants to deliver electrons of its own. In other words, boron always is serving this part nucleophile, part electrophile role simultaneously. It's definitely an electrophile because it wants to be attacked, but as soon as it's attacked, it wants to be a nucleophile, so it kind of wants to do both at the same time. And this is how borane exists. Two molecules of itself will kind of collide with each other and interact in a way to try to stabilize things. So that's the important part. Now let's see if we can't finish off the actual mechanism that we came here for. And again, I'm definitely not going to tell you how this actually works, and the piece I'm about to draw now is complete nonsense. This is definitely not how it works. And I've looked it up before and decided there's no way I want to talk about this. But it's complicated, and what I'm about to draw is nonsense, but it does convey kind of truthiness, if you will. So this H- is going to come and replace this carbon-mercury bond. This is definitely not how it works. This is nonsense. On the other hand, it describes the final product that you get from this, which is to say that you had two hydrogens at this location before, and now you have those two hydrogens just like you did before, and you have now added a third hydrogen from the borohydride, and that's what you end up making as your final product. Why does this video exist? Because borane is weird and borohydride is the source of H-. Does the H- work this way? Well, in the case of borohydride reacting with mercury, absolutely not. But the result is this, as if it had added H- in order to kick out the mercury. So there. Now, in point of fact, I am never going to ask you for the mechanism of how mercury acts
with borohydride.
That would be completely unfair, and I'm not going to ask it. What I want you to know is that if you take a double bond sort of material, like so, and you tell it to react with mercury first in the presence of water as a first step, and then when that reaction is done, you throw in some sodium borohydride, then the result is going to be this product. I would expect you to be able to generate a mechanism for the first parts, and I would expect you to treat the second part like magic, but to recognize that the result of the magic is to replace the carbon-mercury bond with a carbon-hydrogen bond.